Hi everyone, so in this video we are going to do some revisions, okay, and this question is for chapter 2, which is about magnetostatic. Alright, so let's go through the questions together. You have two, okay, infinite line. Infinite line, it means that the line is very long. You don't know what is the length, and this line, okay, and wire, they are placed at the position y at equals to 0 and y equals to 6 respectively. Okay, two wire. So both are carrying same current of 1 ampere, okay, in the same directions. Okay, so the question didn't specify what is the direction, but they just tell you that they are in the same directions. So you have to find the magnetic flux density at the position y equals to 3. Okay, so what is magnetic flux density? Okay, the symbol for magnetic flux density is B. Okay, and you can relate the B with the H by using these equations. Okay, right. Multiply the permeability, okay, with the magnetic field. Okay, so in this case, it didn't specify what is the medium, so we will assume that the mu over here is the permeability of free space, whereby you can get this value, okay, from your calculator. Alright, so since we are dealing with infinite wires, right? So this is an infinite wire. Okay, so this means that we can apply either Biot-Savart's law or Ampere's law, right? So for both the law, it stated that to find the magnetic field, okay, we can apply this formula, which is I over 2 pi r and V. Okay, so I stand for the current and R stand for the distance. Okay, stand for the distance. So first of all, we have to do the drawing. Okay, we have to draw out the wires. Okay, so let's draw the wires. So now let's say here, this is your 3D coordinate systems. Okay, so this is your x-axis and z-axis and y-axis. Okay, where does the wire is located? Okay, so the wire is located at the position y equals to 0 and y equals to 6. Okay, so y equals to 0 is these positions, while y equal to 6 is over here. Okay, so I will draw the wire. Okay, so this is the way we draw the wire. Okay, so this wire, all the coordinate, okay, on the wire, okay, will have the y coordinate equal to 0, and the other wire will be located at the positions y equal to 6. Okay, so question didn't tell us what is the directions of the current, so I will assume myself that the direction of the current is going upward. Okay, so I assume, okay, I is going upward. Okay, going upward. Okay, so this is my own assumption. You can also assume it to be downward. Okay, doesn't matter. Right, so now they are asking you to find the magnetic flux density at the positions y equals to 3. Okay, where is y equals to 3? Okay, where y equals to 3 can y equals to 3 is this part, right? Okay, so means that it can be this point, it can be this point, right? Am I right? So there are so many points. So basically they just want you to find, okay, the value of the magnetic field at these positions. And because the wire, they are infinite wires, okay, so basically all the points here, okay, they will have the same h, okay, as long as their distance from the eye is the same. Okay, so here I will just assume one point. Okay, assume that I want to find the magnetic field at these positions. Okay, so this position is 3. Okay, so this is 6. Okay, so we have to find the total H. Right. Okay, so means that we have to find the H that is coming from wire number 1 and plus the H that is coming from wire number 2. So I will label this one as wire number 1 and this is wire number 2. Okay, so let's apply the formula. So for the H1, okay, is equals to I1 divide 2 pi r and V. Right, so how to get R? Okay, remember we have to find a point T, right? Okay, so where is point T? Okay, so in this case, okay, so the point T, if according to this wire number 1, okay, I will write down as T1. The T1 will be equals to, so all the X, they are 0, and the Z, you don't know what's the value, right? But the Y, you are sure that it is 0. So the Z, you will follow the Z of this, right, of this point. Okay, so this point has a coordinate of 0, 3, and 0, right? So here. Okay, so this is T1. Okay, so let's find the R. Okay, so R equals to P, that is the 0, 3, 0, okay, minus 0, 0, 0. Okay, so you have this 3y, okay, and your R is equals to 3, and your unit vector R is equals to y. Right, so we are going to replace here. So the I1 is equals to 1 over 2 pi r. R is 3. And this phi is equals to, if you remember, the phi is equals to dl, okay, the direction of the current flow, cross product with the unit vector r. Okay, so over here, look at the direction. I assume it to be z direction, so I write down z directions. And cross product with the y, okay, y. Okay, so over here I can see that, okay, my magnetic field, okay, the cross product of this is equals to negative x. Okay, because in opposite rotation directions, so this is negative x. Okay, so I will calculate it. 1 over 2 pi multiply with 3, so I have negative 0.053 x. Okay, so this is my H1, right, my H1. Right, so for the H2, right, so we're using similar method for the H2. H2 refer to I2 over 2 pi r, right, and phi. Okay, so now we are going to figure out what is the T2. Okay, so T2 will be located along, okay, along on this wire number 2. Okay, so for wire number 2, we are very sure that the x is 0 and the y is equal to 6. So we follow the value of z of our point P. Okay, that is 0. So we have 0, 6, 0. Okay, so let's find the R. Okay, is 0, 3, 0 minus 0, 6, 0. Right, so you have a negative 3. Okay, negative 3y. Okay, so R is equals to 3. And the unit vector R is equals to negative 1. Okay, so now again I plug in into my formula. Okay, it should be 1. Okay, the I2 is 1 over 2 pi. Okay, over here I write a 3. But for this, okay, I'm going to cross product the DL, right? Doing this thing. Okay, so the current again is the same direction, it's Z. Okay, Z. And now I have to cross product. Okay, I have to cross product with my negative y. Okay, so as a result, I get x. Okay, so the value is the same, so it will be 0.053. Okay, 0.053 x. Okay, so now let's define what is the H total. So the H total is equals to, okay, you can find from this one, right? So since they are in the different directions, so the H total is equals to 0. Okay, and the B, that is the magnetic flux density, is equals to mu naught multiply with the H. So it is also equals to 0. Okay, so this is the total magnetic field at the center, okay, of this. All right. Okay. So now let us modify the question a little bit. Okay, let us modify the question a little bit. Okay, by topping out this. By topping out this. But here I want to change something. Okay, here is saying that if a circular loop, okay, okay, so this is loop, radius is 1, okay, so this is the radius equals to 1, is added with the center located, okay, at the position 0, 3, 0, parallel to ZY plane. Where is ZY plane? So this is our Z, alright, and this is our Y. Okay, so ZY plane, it means that we are going to have the loop over here. Okay, circular loop over here. Okay, so the center is here, okay, and the radius is equals to 1. Okay, so what will be the directions of the current in the loop and the direction and its value, okay, its value, okay, is value, okay, so that the total magnetic flux is equals to 0. Okay, we all know that just now we have calculated at the position P, this position P, the total magnetic flux density is equal to 0. So here I want to modify a bit the questions by changing the directions of my current. Okay, so here I want to change the direction of the currents. Okay, I think I want to draw a new diagram for this, okay, to show the modifications so that you are not confused with that. Okay, so I redraw again, okay, my parallel wire. So I have one wire over here and another wire over here. Right, infinite wire, and I have one circular loop, okay, in between them, right? And the position P here, okay, is equals to 0, 3, 0. Right, so the current, okay, is 1 ampere here, okay. Just now our current is moving this way, but now I want to modify the questions, okay, so that the current going down, okay, the current going down. So the additional question is asking, okay, what will be the direction of the current flowing in the loop, okay, loop, okay, what will be the directions, okay, and also the value, so that the total magnetic flux density is equals to 0. Okay, so I don't use the same direction current just now, okay, because when I do like that, initially the point P will have a total magnetic flux equals to 0. Okay, so I modify these questions, okay, by topping out a current loop and by changing the directions of the current. So I want you to find out the direction of the current for the loop and the value in order to make the total magnetic flux density equals to 0. So the total magnetic flux density, okay, it would be actually coming from the total magnetic field, right? And in this case, the total magnetic field will be equals to the magnetic field coming from H1, right? H2 and also H loop, okay? So this one refer to the magnetic field, okay, at the position P that is due to the current flowing in the loop. Alright, so we have got the value of our H1 just now, which is negative 0.053, right, 53x. Okay, so for the H2, okay, what you need to modify is over here, right, is over here. So the value of the magnetic field, okay, for the I2 at the same position P will be still be the same 0.053, but because we change the directions of our current, Okay, so it is not z anymore, it is negative z. So negative z and negative y will give you negative x. Okay, so here we will have hash 2 equals to negative 0.053x, right? Okay, so in order to make the PBT equals to 0 or HT equals to 0, okay, my hash loop, okay, should be positive, right? Minus these two, okay, it should be 0.053, okay, multiply with 2, which is positive 0.106, okay, and in the x directions, right? Okay, so when you add the h1 together with the h2 and with the h loop, okay, you will get your ht equals to 0, right? So the question is asking how to get, or what should be the direction of the current, okay, in the loop, and also, okay, what should be the value of it. So in order for me, okay, to get is h loop equals to this. Okay, right? So if you remember, we talked about how to find out, okay, the magnetic field, okay, from the circular loop, okay, in our tutorial sections. If you recall this is the exercise, so you can refer. So this is in your note as well. Okay, so we have talked about this. Okay, we have talked about this, how to find, okay, the magnetic field due to circular loop, okay, that is located, for example, in this question at these positions, right? Okay, so we do the derivation by using the Biot-Savart's law, okay, and eventually, okay, we found that this would be the equations. Okay, so these will be the equations, or for us to find the magnetic field at the center, okay, of the circular loop. So I represent the currents, and A represent the radius of the loop, and Z in this case, why it is Z? Because the loop is located in the XY plane. Okay, so the magnetic field will be in the Z directions, but in our exercise, okay, in our exercise over here, okay, our loop is located at the ZY plane, and from the relationship over here, we know that our H is in the X direction. So basically, we will focus on the value here. Okay, so it means that, okay, to find the H loop, we are going to apply the formula, which is I over 2A. Okay, so we want it to be 0.106 so that the H total is equals to 0. So what should be our I? Okay, our I loop, what should be it? Okay, if my radius is equals to, what's the radius? Is equals to 1. Okay, so I will replace my 1 over here. Okay, so IL, okay, will be equals to 0.106 multiplied with 2. Okay, 0.212 ampere. Okay, so this is the value of the current in the loop. But how about the directions? What should be the directions? Is it clockwise or anti-clockwise? Which one? Okay, so now see, okay, the direction of the loop should be positive X direction. So you have to use your hand, okay? So you have to imagine you are gripping the loop. Okay, so this is the circular loop and you are gripping it. You are holding it. Okay, holding it. So your 4 fingers will represent the directions of the magnetic field, okay, in the X directions. So imagine your hand, your 4 fingers should be turning this loop like this in order to make your magnetic field going out. going out, okay, which go to these directions. Okay, so when your forefinger is gripping in this way, okay, is gripping in this way, you will have a magnetic field, or you have your thumb pointing these directions. Okay, so these directions will represent the directions of your currents in the loop. Okay, so when you're gripping like this, okay, when you're gripping like this, your current will move in the anti-clockwise directions. Okay, so you can either draw it, okay, you can draw it by labeling. This is the I in the loop, and this is your point P. Or you can explain and say that the I in the loop will be in anti-clockwise directions. Alright, okay, so this is how you determine the value, okay, of the current in the loop and also the directions. Okay, so you have to remember this formula. Okay.